I need to relearn the word.
Okay, here we go.
Yeah.
Ready to start. Here we go. So we've been talking about rate of change. Are we ready to start? Ready to start? Ready to start? It shouldn't take that long to quiet down. I've been saying this for 30 seconds now. Ready to start, class? You're still talking. People are still talking. Still talking. Ready to start class? Okay. I understand 5 or 10 seconds, but not 30 seconds, okay? All right, here we go. So we're talking about rate of change of multivariable functions. And we're talking about the different, considering that in the context of our different representations of multivariable functions. So we ended up last time with figuring out what the partial derivatives were looking at the table. Okay, and so the next one would be a contour map, or the level curves. So let's do that. So here I have this function that gives its wind speed in a tornado. As a function of the volume or the size of the tornado and the distance from the center. So distance, this is hundreds of feet. Read this. This is 100 feet, 200 feet, etc. And then volume in millions of cubic feet. 1, 2, 3, 4. Okay. And so, first of all, what is the wind speed for a volcano that's 200 million cubic feet and 200 feet from the center? What would the wind speed be? Can you tell what that would be? What would you say? 75 miles per hour. So you look at 2 and 2, and that puts you here, kind of in the XY plane. And then the contour lines are telling you z values, right? So if you stay on a contour line, you're staying at a constant z value. So these contour lines are every 25. Do you see that? If the black ones are labeled on the 50s, then the red ones would be the 25s in between that. So we'd be at this point right here. It'd be approximately 75 miles per hour. Okay, so then what would it mean to estimate, using this contour plot, the partial with respect to v at 2, 2? So at that same point, what's the partial derivative with respect to v at 2, 2? What would we need to do that? What would we need? Nick, Samuel? All right, Nick.
We need to know the directional vector.
What is v?
Volume on it. If we go into the
Okay, so volume means change in x, right? And what do we? So in order to figure out this rate of change, we need what for a horizontal change on this graph? What would we need? Yeah.
Like a point on one of the lines.
Okay.
Well, on both sides.
On both sides. Okay. So really, in a nutshell, what are we calculating? If I were to write some symbols down here to kind of represent what we're estimating, what would I write? This is just symbols, no numbers. I just want symbols that kind of represent what it is this rate of change means. What would it be? Rate of change. Rate of change. Anybody? Maybe? Emily? No, it has nothing to do with the 0.22. Just in general, nothing to do with numbers. Just what what encapsulates the idea of the partial with respect to v? Yeah.
dw dv.
He wants dw dv. What do you think? That's it. It's right. It's the rate of change of wind speed with respect to volume, and so that's what we're gonna kind of read off from this graph. So no, I should have wrote dw dv equals that, and that's going to be approximately now based on at 2, So we could go to we could go to the next. So we're going this way, right? So what we can do is we can pick a standard dv and then guess what the w is, or we could go to the next w line and figure out what the dv is. It's like either way, you could do it either way. So let's do it this way. Let's force our dv to be, what would that be? 0.5, right? See that? So I'm looking at a dv of 0.5, and I'm saying how much does in each case here, how much does the wind speed change from, say, here to here, averaged with from here to here, for a dv of 0.5? So about how much does the wind speed, does it increase or decrease going this way? Increases, and about how much? 25? 25 would be from here to here, right? That'd be a change of 25 from line to line, from contour line to contour line. So that would be 20. Yeah, and then is that about the same over here too? Maybe a little more, maybe 21, if you want to say 21 or something like that. But it's all estimation. So I think it's fair to just go with 20 for both. Let's do that. So it's like something short of the full distance between contour lines, which is 25. So 20 gives me a rate of change of 40, and then what would that be? Units. Millions cubic feet, right? Nope. Miles per hour? Miles per hour per million cubic feet, right? Okay, so what I want you to do is, so there's another partial derivative, right? The partial derivative with respect to distance from the center. So tell me, in essence, what is that partial derivative? I want you to make an approximation for that value, get the right units, and then I want you to interpret both of these values. Interpret both of these values. And interpreting doesn't mean saying that it's the rate of change. We know that. It's the rate of change. This one's rate of change of speed with respect to volume of the tornado. But what does it mean? What does that number 40 mean? So you got, what is this partial derivative? Do an estimate based on the picture. Get the number, get the units, and then interpret both those numbers. Okay, so you got lots of work to do. Everyone's engaged. You're making progress. 40? There's my estimate. Is it close to yours? So about negative 80 is what I'm coming up with. You come up with something close to negative 80? It's ballpark, right? We're all going to get something different, but it should be close to that. So I'm seeing negative 25 here, and a little like negative 60 here, or something like that, right? Because this is more than two lines. So negative 25, negative 60, or you could even say negative 50, something like that. So it's going to be a little bit more than halfway between negative 50 and negative 25, which is 37 points. So I said negative 40. Yeah?
Why is it negative?
Why is it negative? For increasing distance, what happens to the wind speed? See, it's going down, right? So it's negative. So I'm saying about negative 80. About. And that would be, that's miles per hour per 100 feet. Okay, what does this number mean? It means what?
A small variation in the variation in W will be 40 times as much.
Right, holding what? Holding the big D constant. So you hold a distance constant and speed up the wind speed a little bit, like little dV. Then increase your volume of the tornado a little bit. Then your increase in wind speed will be 40 times that increase in volume. Did you say something like that? Good. So that's what Levada said. Okay. All right. So from here, I'm going to suppose that the volume decreases by 0.4 million cubic feet, and the distance from the center increases by 0.1 hundred feet. So I'm going to let the wind speed go down a little bit, 0.4, and then the distance from the center go up, 0.1. I want you to find the resulting, if both those changes occur, what would the resulting change in wind speed be? So you do it. So what would the resulting change in wind speed be if the volume of the tornado goes down by 0.4 million cubic feet and the distance from the center goes up 0.1 hundred feet, or was that 10 feet?
Yeah. So you have two different vectors there.
So somebody new, how do I do this? How do I get the change in wind speed for these two changes in my independent variables? Kevin, did you get this? How would I get the change in wind speed? What's that? And add up, what are you going to add up? Negative 0.4 times 40? Is that right? Yeah, so the rate of change times the change in your independent variable gives you the change in the dependent. Okay, what else? Negative 80 times 0.1. And did we get a number for that? Negative something. Was it? 24? Negative 24 what? Miles per hour. Okay? And this is all approximate, right? This is all approximate. And so then what would the new wind speed be? So then what would the new wind speed be? About? What's that? Who said that? Angel, how are you getting that? Yeah, so new wind speed would equal old wind speed plus the change. That should make perfect sense. Take the wind speed before, add the amount of change, and you'll get a new wind speed, which is? This is all approximate. 51. So the effects of both of these changes are to make the wind speed go down. Smaller smaller volume and further from the center. That makes sense. That those will both contribute to making the wind speed go down. Okay, so if I'm right here, how can I represent those changes? So what was my change? dV was negative 0.4. How do I represent that change on the picture? What does that mean? Cody? Backward that way, he said. Backward that way. I like it. How much? How far? 0.4, right? And then how do I represent this change, dd 0.1? Up. In what proportion to that backwards that way? 1/4, right? Okay? So I'm taking these changes in combination, and it's kind of like the combination of at a ratio of -4 to 1. Is that right? So if I actually went 1 unit in this direction and found out what the change was, if I actually went 1 unit in this direction and found out what the change was, then that change, that dW, would be the same as the rate of change for that proportion of changes. Does that make sense? So how do I go exactly 1 in that direction? How do I go exactly 1 in that direction? What would the... It'd be like a vector, right? What vector would that be that goes exactly 1? Tell me. What is it? What's the magnitude of the vector? Radical 17, right? So I'm going to go up here. So now suppose I want to go, so at that rate of 40, and now what? -4 over square root of 17 plus -80 times 1 over radical 17. Now that, because the amount that I'm going in combination is now 1, kind of 1, right, as a unit vector, this is also equal to the rate of change of taking those changes in this proportion. -4 in the x direction to 1 in the positive direction. Why? Because those are 1. Does that concept make sense? So taking these changes in that proportion, -4 to 1, if I find the amount of change dW where my overall change is 1, like a unit vector, like you said, then that change in W will be the same as rate of change, right? Because rate of change is the change in W per 1 unit. And we're going 1 unit. Okay, now take a look. So this looks like what vector operation? Multiply plus multiply. What is that like? Dot product of what 2 vectors now? 40, comma, -80. What are those? Where do those come from? Partial derivatives, right? So this is a vector of partial derivatives. And then the second vector would be? Unit vector representing some proportion of changes of an x and y change. Are you following this? So in general, the rate of change is equal to a vector of the partial derivatives dot a unit vector that's representing a proportion of changes in x and y. This vector of partial derivatives is called, the gradient vector. It's written this way, upside down triangle. And the notation for this rate of change is big D for derivative in the direction of u of the function f. So what have I allowed for now? I've allowed to, what I'm figuring out now is any rate of change for any proportion of two changes taken together of our independent variable, in this case, volume and distance. So this is called the directional derivative. By allowing any proportion of changes of my two independent variables, I can get a unit vector in any direction, right? So before we were focusing on just two rates of change, the rate of change in the positive x direction and the rate of change in the positive y direction. We can get a rate of change for any proportion of two changes taken together. And so that proportion indicates some direction. So every direction here from our focal point represents taking two changes together in some proportion. All right, so you're going to find the direction, the rate of change in any direction. You'll take the gradient vector, which is a vector of the partial derivatives, dotted with a unit vector in the direction that you're interested in. So here our direction was -4 to 1. What's another way to specify that direction? What's another whole different way to get that direction? What one quantity could tell us the direction, any direction from a point? Angle, right? Angle measure. So with an angle measure theta, there's some angle measure theta that gives it that proportion, -4 to the right and 1 up. And so our unit vector, if we had theta, what would the unit vector be? How would we get the x and y components of that unit vector given the angle theta? What does that? Yeah, some.
No, rad 17, cosine theta.
But we want a unit vector, right? So we want it to be magnitude 1. So it's just going to be cosine theta. Someone else said sine theta. That's what those do, right? Cosine and sine give you a point on the unit circle. Distance 1, unit, right? X coordinate, y coordinate of the unit circle. So however you can get that unit vector in the situation is fine. Either it's going to be an angle from an angle, and you can use cosine and sine, or some other way you have the two components and you find the unit vector from the components, like the way we did it first. Okay, so let's look at another example here. Any questions on these partial derivatives, or we're transitioning to this idea of that there's a derivative or a rate of change in any direction represented by taking two changes together. Any questions? Okay, so let's look at this. So here I have a contour map over here to the right. And just coincidentally, I'm focusing on the same point, see the point 2, 2 over there. So now I'm interested in a rate of change in any direction from that point. So we know that the rate of change straight to the right is, how do we symbolize that? Or what do we call that? The rate of change in this direction? Partial with respect to x. And then we know the rate of change straight up is partial with respect to y. But now we're talking about getting a rate of change in any direction from this point. Okay, so we can throw a unit circle around that point, and then I can put that same unit circle down here. So that's the point 2, 2, right? So here's the point 2, 2, here's the point 2, 2. And we're going to consider a unit circle around that point. And then we want to look at that on the surface. Here's that point on the surface. Oh, let me give you the function here. The function is, if I can read that, 4 minus 1/2 x squared minus, and we're going to call this g of x, say g of xy equals 4 minus 1/2 x squared minus 1/4 y squared. That's, this contour plot gives that as a one representation over there on the right, and then the surface is the gold surface, another representation of that function. And I'm going to focus in on the point 2, 2, and we're going to think about picking a direction, right? So picking a direction from 2, 2. And so where's that up here? Scroll this one maybe? Yeah. So notice what I'm showing on both screens is the same. What theta is that right there? It's our standard trig angle. It'll be theta equals positive x-axis, 0, right? This would be theta equals pi over 2. Pi is there. So you see I'm showing the exact same thing on both graphs. This is the direction of positive x. That's theta equals 0. Positive y, theta equals pi over 2. Pi, 3 pi over 2, 2 pi. Okay, so I want you to find, this is the angle pi over 3. Theta equals pi over 3. I want you to find the rate of change of this function in this direction, where theta is pi over 3.
This of the curve is sloped downwards, which makes it more negative.
And so,
It opens downwards.
what's that?
It opens downwards, so it makes sense that you're.
So that's the result of just an overall quality of the surface, is what I'm hearing you say? Just because it's concave down, so then it should be negative?
At that point with that angle.
Yeah, right. Right, exactly. So in this direction. Yeah, right. So in this direction. So it's like you're on the side of a mountain. If you took a step in that direction, what would happen? You go downhill, right? You go downhill a little bit, okay? So, what was I going to say? Oh, and so what is this? Our unit vector, that cosine, you can use cosine of pi over 3, sine pi over 3. But really what that is a proportion of changes, right? dx to dy in what proportion? Or dy to dx, proportion of changes is? Radical 3 to 1, right? It's like if you change x a certain amount and change y by radical 3 times as much as that, there's a rate of change for taking those changes, right? And that rate of change is a negative 1 radical negative 3 over 2. Right? So if this was a real world situation, like the ones we've been seeing, so if you take your independent variables, those changes in this ratio, then the overall rate of change to your dependent variable will be this. Okay? So, does that make sense? Okay, so let's take this conversation a step further. Any questions on that example? Okay, so this is the directional derivative. Derivative in the direction of theta is the parcel of x times cosine, parcel of y times sine. That's the dot product. We did all this. And so then that's the gradient of whatever our function is, dot this unit vector. So there's another way besides multiplying components and adding. There's another way to find the dot product. What's another way to find the dot product? Remember? Besides multiplying like components and adding, we had another way to compute the dot product. What was that? Product of the magnitudes times the cosine of the angle. Now, is that cosine of theta? Well, yeah, you can read that it's alpha. But is that the same, is that cosine, is that the same angle as theta? What is theta? Theta is our chosen direction reference, or as the standard trig angle from positive x, right? If you're doing that dot product, what angle is that talking about? Right, this is the angle. Alpha is your angle between the two vectors, in this case the gradient vector and our chosen direction. So we need a different, it's not theta. Theta defines the unit vector from the positive x-axis, right? Theta is swept counterclockwise from the positive x-axis for the unit vector. Then now we're doing the dot product. Alpha is the angle between the two vectors in question. So it's the angle between u and the gradient vector, whatever that is. Okay, so why do we care about that? Well, so then therefore, since the unit vector has magnitude 1, you can calculate this as the magnitude of the gradient cosine alpha. Okay, so we're on the side of the mountain, and now we have, how many rates of change do we have that we could possibly? An infinite number, right? Depending on the direction that you turn on the side of the mountain. So that kind of begs a question. Like, of all those rates of change, which one is? Which one is the greatest, right? The best, right? I like this rate of change. No, the greatest, right? So which way, like on the side of the mountain, there would be one way you could face that it would be the steepest, right? Greatest rate of change. So that's what we're interested in, finding the greatest rate of change. We want to know the maximum value of this. So how is this made maximum? So there's our rate of change in any direction. What would the maximum value of that be? So what's variable here? Yeah. How do I get that to be the biggest? What's the biggest cosine alpha can be? No, pi over 2 is a value of alpha. What's the biggest the cosine can be?
1.
1. Right? So the max value of that is 1. Therefore, what's the maximum value of the directional derivative? Magnitude of the gradient is the biggest rate of change that you can have. I think so too. So when cosine alpha equals 1, that gives you the biggest value of all those rates of change that we could have in all directions. The biggest one you get is the magnitude of the gradient. Okay, now what direction should we go to get that? What direction should we go? Now I'm asking about alpha. So what should alpha be to get a cosine of 1? We want that to be 0, right? And what does that mean for our vectors then? If alpha is 0, we're saying the angle between these two vectors is 0. So how should I choose u so that alpha is 0? Yeah.
Have it u be 0.
No.
Oh, 1 0.
No, remember what alpha is. Alpha is what? It's not theta. It's not theta. Alpha's not theta. What is alpha?
It has to be in the direction of F, but you
In the direction of
observe the
gradient,
gradient.
right? So alpha is the angle between those two vectors. If I want that angle to be 0, I'm going to choose my u to be the same direction as the gradient. See that? So this maximum rate of change is all about the gradient, right? The value of the max rate of change is the magnitude of the gradient vector. And the direction of that max rate of change is the same as the direction of the gradient as a vector. So let's see that in our previous example here. Okay, so here we are. So let's just eyeball it first. Like what quadrant would our direction of max rate of change be? So here's quadrant 1, quadrant 2, quadrant 3, quadrant 4. So which quadrant was going to be the direction of max rate of change? 3. Something over here, right? Something over here. Well, it's all about the gradient, right? What was the gradient at 2, 2? So G, the gradient at 2, 2 would be what? What was our gradient? It was negative x, negative 1/2 y, is that right?
Yeah.
So at 2, 2, what's the gradient? -2, -1. Because it's negative x, negative 1/2 y. Was our gradient function, and so then at 2, 2, -2, -1. Does that make sense for third quadrant? Yeah. So it's actually right here. Where is it? It's right there. So this is actually the vector in the direction -2, -1. Okay? And look, and so if you go that direction on the side of the mountain, you're going to go up the steepest, fastest. Okay? Now look over here in the contour plot. What do you notice about that direction of max rate of change in the contour plot? Notice anything particular about that compared to the contour lines? Notice anything? No, but I'm asking, we're talking about the direction, right? The direction of this compared to the contour lines. You see that it's orthogonal? Why does that make sense? Why does going orthogonal to the contour lines give you the max rate of change? Why does that make sense? No, not quite. Not cross product. Why does going orthogonal? Because we're talking about going up the fastest, right? How would you get to the next contour line the fastest? Go orthogonal, right? So you want it to get to that next contour line the fastest, you would want to go orthogonal to the contour line, right? If you go on an oblique angle, it's gonna take more walking to get up to that next contour line. So orthogonal to the contour line gives you max rate of change. What about maximum negative rate of change? Or the steepest downward? So what is the max negative rate of change, first of all? So that'd be what? Right there, right? Wouldn't this be the direction of max negative rate of change? And what would the rate of change be? No, the rate of change. So yeah, so we were talking about direction, and we lost sight of the actual rate of change. The actual rate of change in the max rate of change was, do you remember what it was? What we said? We said the magnitude of the gradient. Remember that? Gave us the max rate of change. So what is the max rate of change in this case? Square root of 5. The magnitude of our gradient vector in the direction of the gradient vector. Okay, so the max negative rate of change is going to be the opposite of that, right? It's going to be the opposite of that. And in what direction? Won't it be exactly the opposite direction? So the gradient at 2, 2 is negative 2, 1, so it'll be in the direction 2, 1. First quadrant, right? Okay.